Okay, so today we're going to talk about strong versus weak acids and the neutralization of an acid. So first off, let's talk about strong acids. Strong acids are any acid that will dissociate fully and completely react with the base. So it's going to dissociate fully in water and will completely react with the base. So it's an acid that will essentially dissolve. You can think of it that way, but acids are already liquid. They dissociate completely in water. What that means is that the functional part of an acid is really the H plus ion, right? The anion, or the negative half, really doesn't do anything. There are always spectator ions, or almost always. So the functional part of all acids is really the H plus. Therefore, if it fully dissociates, that's going to give us more H plus to react in the solution. Regardless of what the acid is, whether it's HCl, HBr, HI, H2SO4, they all react the same way because they all donate the same thing. They will all donate H pluses. So it doesn't matter really what it is, what the parent compound is, because they all donate the same exact thing and they all become the same thing. All right. There are 6 strong acids in the world. Unfortunately, you'll have to memorize them. Yeah. You will have to know these 6 strong acids. HCl, H2SO4, HBr, HI, HNO3, and HClO3. That's actually supposed to be HClO4. So if you can correct that, it's supposed to be HClO4. But I am trying to do that. And hold on. Let me back. Hold on.
Is that HI?
Yeah, it's HI. Hydroiodic acid. Are you guys just going to take pictures? You guys are so...
I'm still behind right now, so I was trying to do that.
That's a 4.
Give me a second.
There we go. Okay. That's a 4. HClO4. I know. I don't know what I was thinking. Okay. It's not a link. I hyperlinked it. All right.
The hyperlink doesn't work on that.
Okay, good. Yes, no? No? Okay. So, strong acids are going to fully dissociate. It means that a strong acid will donate more H+, which means that you'll get more H+ in solution and more like acidic punch or bang for your buck. All right. So, here's an example of our strong acids, HCl and NaOH. So, we've done this probably 1,000 times before, but we'll do it another time. When we do the net ionic equation, we've got H plus Cl minus plus Na plus OH minus. I'm running out of room, so we're going to pretend like our reaction arrow is pointing down, even though we would never do that. All right, and that's going to form water and Na and Cl. Okay, so here's our reaction. It's kind of a weird little boxy reaction because I write big and I didn't borrow the stylus from Mr. Prost. It is Na. Oh, my bad. Thank you. It is Na+. All right, so we can remove all of our ions that appear on both sides. In fact, I'm just going to erase them because I think that might be easier. Boop-a-doop-y-doo. Erase those, and then notice we have a very sloppy reaction, but it's essentially H plus OH yields H2O, correct? Any questions on this? We've done this quite a bit before.
Will all acids basically dissociate to this?
Most will. Not everyone, but most will.
Like
We'll see that in a second. All right, here's another example. I'll give you a gigantic hint. It does the exact same thing. And here's the third example. Huge hint. Same exact process, all right? Sorry. We only did the first one because I don't want to spend time doing all of these when they're the exact same thing. I have the utmost confidence that you can all do this. Good? Questions? I will wait 1 second. All right? No? Yes? I don't know when we're ready. What? All right, weak acids. Weak acids. Weak acids are the opposite of strong acids. All right, they're the opposite of strong acids, which means that they do not fully dissociate in water. So they will not fully dissociate. So we're not going to get that full H+. A lot of it won't break apart. So they're not going to distribute as much H+ as a strong acid would. A strong acid will completely break apart, and it will donate all of its H+. A weak acid won't. Only some of it will, or very little of it will. So they don't break apart as well. Since they don't dissociate fully, in a net ionic equation, we can't break them apart. So because they don't dissociate fully, we can't break them apart. And we're going to show you, or I'm going to show you what weak acids look like in a net ionic equation. It actually makes the equation a little bit longer, but it's actually easier to do. Okay? So you might ask yourself, how do I know if it's a strong acid or a weak acid? Well, the good news is if it's not strong, it's weak. Since there are only 6 strong acids, every other acid in the entire universe is weak. All right, so if it's not one of these 6 strong acids, it's a weak one. All right? Not too bad? We're almost done with, we're flying through these notes, so don't worry too much. Okay, so let's do a couple examples. Okay, so here I have phosphoric acid and sodium hydroxide. Phosphoric acid and sodium hydroxide. So, first off, phosphoric acid. Do you think that's a strong acid or a weak acid? Weak, yeah. There are 2 reasons you know it's weak. What's one reason I know it's weak? It's not one of the strong ones. What's the other one? It's on the slide entitled weak acids, right? Because context clues will tell me that if it's on the slide saying weak acids, yeah, 9 times out of 10 it's a weak acid. Okay, so I cannot fully dissociate this. That means in my net ionic equation, you know how we were used to writing H+? We can't. We have to write H3PO4. Because it doesn't break apart in solution. Remember how we said that if it doesn't dissolve, we can't break it apart? Remember when we were first learning net ionic equations, we had to look at the insoluble one, and that one doesn't break apart? Well, think of weak acids as kind of insoluble. Think of them as insoluble. Now, they'll still behave like an acid. They'll still behave like an acid. So what's one of the products of this reaction? Water. Water is almost always a product of a reaction. What's another product of the reaction? Not exactly. Take a look. If I have one H going over to here, so I have an H from my H3PO4, just H2PO4. No, even if I did have an Na attached to it, it would be dissociated in water. All right? So take a look. What's formed is water, because water is a primary product of an acid-base reaction most of the time, because one of my H's was donated from my phosphoric acid. And since only one went over, I'm left with H2PO4 and not an Na, okay? Now, Na is a spectator ion, right? So Na will not appear in my overall net ionic equation. So it's just going to be H3PO4 plus OH yields H2O and H2PO4. Does everyone kind of understand what's going on with this? All right, let's try another example, because that's how we learn. Hey, here's a fun one. Does anyone know what acid that is?
That's acid.
It's acetic acid. It's acetic acid. Yeah, it's vinegar. Okay, so I'm going. Oh boy, messed that up. Drew lines. Okay, so I'm going to have my acetic acid. What's it going to react with?
K plus OH.
Yeah, K plus OH minus. By now, hopefully you guys are a little comfortable with the fact that K is probably going to be the spectator ion. So I'm just not even going to write it because it's a spectator ion. So we'll just leave it out. It'll help make this shorter because clearly I'm going to run out of room. Okay. H2O, very good. And then what else? Yeah, my other one is going to be CH3COO. H2O and CH3COO. I know it's kind of blocked by the Docere desktop trial watermark. All right, because look, this H right here, this moved over to this OH to make H2O. All right, that's why it's written like that. That's why the H is put off all by itself, because that's the H that will be donated in solution. All right, they put that H on the end because that means that that's the H that will be given up or donated when it reacts with the base. All right? Kind of get what's going on? The take-home thing is when it's a weak acid, we leave it as it is. It's still an acid. It will still react the exact same way in solution, but it just looks a little bit different. The last one I'm going to leave, and I'll let you guys try it out on your own if you'd like. But I'm not going to spend time because it seems like you guys pretty much get what's going on. Okay? Good? Happy? Everyone all set? You ready? Get set. Hey, let's talk about water. Let's talk about water. Okay. Water is super duper cool. And water is cool because it can be both a base or an acid. So it can be both. It's neutral, but it can act as an acid or a base. A lot of things are neutral and just not an acid or a base and nothing like it. Like, it's kind of like oxygen gas. Oxygen gas is neutral, but it's not an acid or a base. It's just something else. Water is neutral, but it's both an acid and a base. And it depends on what situation we put it in. Can someone please tell me, take a look at this. Can someone please tell me what acid probably is in this case?
H3PO.
Which one's an acid, you mean?
Yeah, which one's the acid?
H3PO.
So what would water be? Water's the base, okay? And in a base, what's the definition of a base? A Bronsted-Lowry definition.
It's a pH lower than.
It's what? It's a proton acceptor. That's right. A base, according to Bronsted-Lowry, is a All right, so we're going to kind of practice this out, and then we're going to try it. So try it on your own, and let's see how you do.